Well, welcome everybody to our webinar, the third in a series in analyzing the American Community Survey and the census with R. This is our third webinar today, focusing on mapping and spatial analysis with the census. The first two webinars that we had dealt with analyzing the 2023 American Community Survey. That was 3 weeks ago. And 2 weeks ago, we had analyzing the 2020 census with R. And the star presenter here today is Kyle Walker, professor of geography at Texas Christian University. I'll say a little bit about his bio later. And this webinar is being hosted by the Social Science Data Analysis Network at the University of Michigan that I'm the host of. My name is Bill Fry. This is really a treat for us to have these webinars. We have a huge crowd today, as in the previous two, so we know there's a lot of interest in them. It's one where you don't have to have gone to the first two webinars to get a lot out of today's. It's self-contained. But if you want to go back to the two webinars, we're going to have them. I believe we now have the first two on our website that you can look at, but we're going to send out an email to everyone in all three of the webinars in a few days so that you can look at the recording of each of them. Each of them are self-contained, so you can just watch one of them. But if you'd like to really get full immersion into the whole process, you can watch all three. Today's, though, is going to be really interesting because Kyle has told me ahead of time that there's a real big finish to it. So there's going to be a lot of interesting stuff all the way through. It's a 3-hour webinar. We'll go till 3 o'clock Eastern time, or you can translate that to whatever time zone you're in. And after each hour, there's going to be a 10-minute break. As I said, Kyle is a professor of geography at Texas Christian University, but he is probably the leading expert in how to analyze US Census data products with R. A lot of people know about R. A lot of people know about census data products, but to put them together with the kind of programs that he has and the tips that he's put together in his consulting and in his teaching, we're just so grateful that we can have his time to do this today, and you're going to get a lot of valuable information. He also has authored this book, Analyzing U.S. Census Data, Methods, Maps, and Models in R, which you can get on Amazon, and he'll say maybe a little bit more about that as well. So he has a lot of good resources that you can develop, not only from our webinars, but from his publications as well. We at the Social Science Data Analysis Network at the University of Michigan have been doing all kinds of webinars and workshops and websites over the years to allow teachers and students and researchers to get access to census data at all levels, whether it's just a first-year introductory sociology course that wants to introduce a couple data analysis modules in their class, up to now using this very sophisticated software in order to analyze R for your research or for your teaching purposes. So, without any further ado, I'm going to introduce Kyle. As I said, there'll be 3 hours, but a 10-minute break after each hour, and you can certainly ask questions along the way on your website. So take it away, Kyle.
All right. Well, thank you so much, Bill, for the generous introduction. As always, thank you to the University of Michigan and SSDan for hosting me. We've had a great partnership over the past several years. And the support of SSDan allows me to offer these workshops to the community for free. And I've seen and I've heard from so many of you over the years of the things that you've learned and applied in your own work. And so for those of you who have never attended before, I'm very excited to have you all join me today, in part because this is a topic that really is the topic that brought me into working with census data. I'm a professor of geography, and the geospatial side of things was always how I really thought about and started working with census data way back when. And so I'm going to go ahead and share my screen and just talk you through a little bit of setup with respect to the workshop today. So Today's webinar is titled Mapping and Spatial Analysis with US Census Data in R. And, Bill gave a generous introduction, just a little bit more about me. Again, I'm a professor and I chair the geography department at TCU. I also work broadly as a spatial data science consultant. I've developed a variety of different open source software packages, some of which are focused on census data, some of which are focused on mapping and spatial data. Now, you'll get a taste of a few of them today. And my book, which came out a couple years ago, um, is titled Analyzing US Census Data, Methods, Maps, and Models in R. So you'll notice here just a couple things in terms of housekeeping before we jump into the specifics. So there were two other webinars if you missed them. As Bill mentioned, he's going to send out a link to the recordings of all of the sessions, and all of the materials are posted online for you. So if you missed the prior two sessions and you're interested in learning a little bit more, so 3 weeks ago, we covered analyzing data from the 2023 American Community Survey. 2 weeks ago, we covered decennial census data, and then this is the third and final webinar in our series. So thinking about getting set up, because as you notice, I've got slides up and some of you like to follow along, I want to go ahead and start posting some links. So take a look at the chat. I'm going to start sharing a few things that you might be interested in for the purposes of today's workshop, and then potentially other learning resources. So first and foremost, paying attention to the chat, this slide deck that I'm working off of is indeed interactive. And so I'm going to copy over the link to the slides. It's kind of a heavy HTML file, just to warn you. We have some interactive maps in there. So just a heads up if your internet connection is a little bit slower. But I'm going to paste that into the chat right now. This is the link to the slides. So if you'd like to follow along, go ahead and follow that link. That specific link will bring up these slides, and you go through the slides by pressing the arrow key on your keyboard, or if you're on a mobile device, you should be able to swipe through the slides. So that'll get you access to the slides. We're also going to be working quite a bit with code today. You're going to be learning how to analyze and map, in particular, census data using R. And so how do you get up and running with R? We're not going to spend time today learning the fundamentals of R. That's something for another workshop. But I do have materials prepared for you that can hopefully get you up and running independent of where you are on your learning journey. So all of the workshop materials for really all three workshops are hosted on GitHub, which, if you're not familiar with GitHub, is the premier or most significant place that people host open source software. The link that will take you to this website that's up here on the screen, I just sent it to the chat. So if you follow that link, you'll get some instructions for downloading or accessing the workshop materials. So I have links here in the README file to all of the slides. So there are a couple different ways to access the materials for today's workshop. And I have this section here that says how to get the workshop materials. If you're brand new to R and RStudio, again, we're not going to cover installing those programs. I'll mention them briefly in a little bit. But if you're brand new, or you just don't want to worry about setting up any sort of environment on your own, follow this link. So what I'm going to do here is I'm going to grab this link and I'm just going to copy it. And I'm going to jump into a different Chrome window here and say, hypothetically, I am interested in working with R. I've never done that before. I'm going to follow this link. It's going to take you here to this Posit Cloud login. And so you can log in with Google. You can log in with or you can just sign up for an account by putting in an email, a password, and a first and last name. It's really entirely up to you how you want to do that. I could sign in with, one of my many Gmail accounts, as I'm sure many of you have Gmail accounts as well. I can just go ahead and sign in. And so we'll get that signed in real quick. And so you'll notice here that the project gets deployed. And so what it's doing is it's downloading all of the materials from my workspace to your workspace. And so this will just take a few moments. And again, if you're working off of R on your own local computer, you don't need to worry about this. But this is going to boot up an R session that exists in the cloud for you. And so you'll notice it should be titled SSDan Workshops 2025 Kyle Walker. You see here a cloud instance of R Studio, which is the premier integrated development environment used for R. There's some newer IDEs that some of you might be using as well, but R Studio has been around for quite some time. You'll notice first things first that you'll see where it says here temporary copy. That means that any work that you would do right now would not get saved. So what I'm going to ask you to do is click Save a Permanent Copy, which will then copy all those materials over to your account. And you'll be set up with a free account if you signed in just the way I did. There's nothing that you have to pay for. You'll click then to access the workshop materials where it says here, UMich Workshop 2025. And I'm actually going to make this a bit bigger, close this out so you can see a little bit better. So you'll click the Files pane here, and then you'll click UMich Workshop 2025. You'll find that the materials for the previous webinars are in this folder. What you're going to do is click Mapping. And then the mapping code.r file, that's your script that we're going to be using today. Now, I'm going to be working off my local computer today and my local version of RStudio. If you want to match what my program looks like, I'm going to ask you to do this. Click the Tools drop-down menu, click Global Options, click Pane Layout, and then move the console to the upper right. So I have clicked this drop down on the upper right and chosen console, and I click OK. I personally like to have my script editor over here on the left, and then my console, which is like a little computer terminal or calculator or what have you, whatever analogy makes the most sense, that allows you to execute R directly. That's going to be over on the right. I like to have that. And so you'll see here kind of my RStudio is going to look like this. I'm going to work through that, but it's going to be a similar appearance. So hopefully that gets you set up if you have never worked with R before. Alternatively, if you have worked with R before, I'm going to jump back over here and I'm going to close this out. If you're an advanced user who's familiar with Git and GitHub, you can clone the repository to your computer. And so by using this command, if you already have the repository initialized from one of the prior two webinars, you can use the command git pull, and that will pull down all of the new materials I've since published. Now, if that is still a little bit too complicated, but you don't necessarily want to mess around with Git and GitHub, but you do have your own version of R installed, what you can do is scroll up and find this mapping folder, click there, and you're going to notice that the R code is available for you. You can click there, and you'll see the code here. Find the little download button to download the raw file, and that will pull that down to your computer, and you can open it up in your own RStudio. So regardless of where you are in your learning journey with R and some of these tools, hopefully there's a solution in those three different options that can get you up and running. All right, excellent. So let's go ahead and jump back here to the slides and talk a little bit about the agenda for today. So in hour one, we're going to talk about the fundamentals of getting spatial US Census data, defining what that is. You'll learn a little bit about how spatial data are represented in R, how you can access spatial census data using R and the tidy census R package. So that'll be hour one. Because we do a little bit more setup in the first hour, we will probably go all the way to the top of the hour. So that'll be about 1 p.m. Eastern time. We will then take a 10-minute break. I'll have a couple exercises for you to do if you'd like. In hour two, we're going to learn about a brand new R package that I've developed in the past year called mapgl. And this is one of my favorite R packages that I have ever developed, one of my favorite projects that I've ever worked on that brings high performance web mapping to R. And I think we're going to have a lot of fun with it. So you're going to learn all about different ways to map US Census data using interactive mapping tools in the mapgl package. In hour three, we'll delve more into some advanced workflows. And so I think this will still be of interest to those of you who are newer to R, newer to some of these tools. If you don't understand all of the code in this section, you can still run it. It will be available and then use it as a learning resource as you continue to build your skill set. For those of you who are more advanced users, this covers some use cases that come up from time to time. How do you visualize time series information or change over time in the census? How do you map the entire United States? That's not always an easy thing to do, especially on an interactive map. So I'm going to show you some recommended workflows and tools that you can use to do that effectively. In terms of other resources as well, before we really start diving in, I'm going to post a few ways that you can connect with me and communicate with me online. So I post to 3 different social media platforms, though I cross post to all of them, so you don't need to follow me on all of them if you'd prefer. I'm active on LinkedIn. I am posting my LinkedIn profile. Feel free to connect with me. I'll accept your connection. And I post a lot about census data, demographics, and then related data science tooling on that page. The best place nowadays for our content is Blue Sky, which is a smaller social media network, but it's rapidly growing. I have a profile there. You can give me a follow. And then for those of you who are on Twitter, now branded X, I still do post there as well. You can give me a follow over there. The last thing that I would recommend, and this is for those of you who are really interested in this content, want to get information about new updates in some of my R packages, other workshop and training opportunities, and updates on blog posts that I write, you can subscribe to my mailing list. And that link is right here. So feel free to connect. I've got about 1,500 subscribers on there, and they get the latest news on anything that's going on with some of these materials. So there are a lot of different ways to stay in touch. Feel free to connect and let me know what you're working on. All right, with that in mind, let's dive in a little bit to US Census data. For those of you who attended the first 2 webinars, some of this will be a little bit of review, but I want to make sure that everyone who's attending today has the same baseline vocabulary with respect to the data that we're working with. So chatting a little bit about it, we're working today with the programming language R, which is a software environment and programming language that was really designed to do data analysis, but as you'll see, there are a lot of other things that it can do. R Studio is an integrated development environment, or IDE, which is a software that really makes it easier for you to work with R. That's what we're going to be using today. And then we have the Posit Cloud environment as well for those of you who would prefer to use that. So We talked a little bit about our studio setup, and we're going to dive in a little bit more now to census data. So there are a couple main data sets that you often will work with respect to United States Census data. There are many, many different data sets that you can access and use, but the main ones that we'll be talking about today include the decennial US Census, which is a complete count of the US population mandated in the Constitution. It's conducted every 10 years. So the last one we had was in 2020, and it is used primarily for proportional representation and redistricting in US Congress, but it also used for resource allocation, a whole lot of other things. It asks a limited set of questions about, say, race, ethnicity, age, and housing tenure and sex. The American Community Survey is another one of the Census Bureau's most important data sets. And this is where you'll get information not available in the decennial US Census. So, income, education, language, those sorts of topics. It's an annual survey of about 3.5 million households, and it's available. It comes out every year. So, we get new data every year. It's available as both 1 year estimates, which come out every year, that cover geographies of population 65,000 and greater, and 5 year estimates, which go all the way down to the census block group. I'll explain census geographies in just a moment, but that'll give you uh, a, a pooled sample, or estimates from a pooled sample over 5 years. And those data are, because they're based on a survey sample, delivered as estimates characterized by a margin of error. So how do you get census data? The main data portal from the census is data.census.gov. I do find it to be quite good. What we're going to be focusing on today is something called the Census API, or Application Programming Interface. And this allows developers to write code to access census data. And that can streamline your work significantly, as you don't have to spend time clicking through menus. And we're not going to make raw requests to the Census API. Instead, we're going to use the Tidy Census R package, which is a package I first released, crazy to think about, 8 years ago. And it's been downloaded over 600,000 times from the POSIT Cranmere since then, used many, many more times than that. And it is a unified and kind of standardized interface to the decennial census and the American Community Survey, and then a select number of other census data sets, some of which we covered in previous webinars. So feel free to check those out. So some key features in Tidy Census: it integrates well with data wrangling workflows with the tidyverse, which is a popular and widely used data wrangling framework in R. Important for today, it automatically downloads and merges census geometries to data for mapping. And I was first inspired to really think this through way back when I first started teaching at TCU. And I came in and I'd been working with census data for years, and I taught Introduction to GIS here at TCU. And I gave students an assignment where they were tasked with working with census data, and they had to go and download the shapefiles and download the demographic data in CSV format, unzip everything, load it all in, merge it together, do type conversions of the columns. For those of you who have worked with census data in a GIS environment before, this will likely be familiar. They struggled mightily with this, because any little thing that you do wrong can trip up the entire workflow. And this was something that I had gotten accustomed to doing over the years, but I started thinking, you know what? This is relatively tedious. I'm doing the same thing over and over again. I'm spending a ton of time doing that before I actually get to the point that I can do analysis. What if we had software that could just do it for you? And so what Tidy Census does is it automatically downloads those census geometries for you for mapping. And so it has a number of analytic tools as well to support census data workflows, and it allows you to look up states and counties by name rather than remembering FIPS codes. This is helpful to me. I know the FIPS code of my state of Texas in my home county. I don't really have any others memorized, maybe a couple. And so this translation that the package does can be quite helpful. And so we'll learn how to do all of that today. To get started, you can install some packages. We'll be working with Tidy Census, a little bit with tidyverse, mapview and mapgl for mapping. If you're using the Posit Cloud environment, these packages are already installed for you. You don't need to run this code. Last thing, and then we're going to really start getting into this. Tidy Census can be used without an API key, but this limits you to 500 queries per day. So you may think 500 queries sounds like a lot for power users. They rapidly approach this 500 query limit pretty quickly. So if you would like to get a key, it's not required to run the code for today's workshop, but I do have the link represented here. I'll probably copy paste that um, for you. You'll see this page. You just put in organization name and email address. I'm going to paste that link for you here in the chat as well, and you can go ahead and request that key. Once you've activated your key, you can use the Census API key function to set that or install it in our environment. And if you specify the argument install equals true, then R will remember your key for the purposes of future sessions. All right, let's talk about the good stuff, getting spatial census data. So spatial census data the old way. I kind of mentioned this a little bit. Traditionally, the traditional process for getting spatial census data required, so you have to go to the census website and fetch shapefiles. You need to download a CSV file and then often clean it up and format it in Excel before you use it. You then have to use a GIS and load your geometries in and load your data. And then you need to align your key fields. And this is something that always tripped up my students, because one of the columns that you need to match on would inevitably be formatted as characters or strings, and the other is coming in as a number. And so that doesn't match. And then this is a process that you would have to do over and over again. So Tidy Census aims to automate this for you. So your core functions in Tidy Census are get decennial for decennial census data and get ACS for ACS data. And required arguments are geography and variables. We do spend more time delving into this in the first two webinars. So if you didn't attend those and not everything is registering, feel free to check those out as well. I see one question, where can we find the key to enter in the program? You don't need a key for the purposes of today. So if you follow the instructions on the previous slide, you can get a key for future use, but for today, you aren't going to need that key. So I want to jump over to our studio here and make that just a little bit bigger so you can see it. What we see here is I'm going to load in my packages, and I want to talk through with you how all this works. So for those of you who are brand new to R, I've been throwing out a bunch of vocabulary, function, argument, variable, and you might be saying, hold up a second, what does all of that mean? Let me just talk through that real quick. So in R, we use something called variables to store information, and we give that variable a name. So here I'm creating a variable called Texas income. This little arrow sign, which is going to be your caret and then dash, that is an assignment operator. And this basically means create an object named Texas income that is the result of whatever this little mini program is. And so get ACS is a function. You can think of a function as a little mini software program that does a variety of tasks for you. Arguments then are going to be the options that you set within the function. So you're basically saying here, make me an object named Texas income that is the result of fetching data from the ACS for where the geography is the county where the variable is this specific variable ID. The state is Texas, and then the year is 2023. To execute this code, there are a variety of different ways to do it in RStudio. What you can do is you can click and drag to highlight a block of code, and then you can click this run button. And what that will do is it will send the code over to your console. So watch this. I just grabbed my data. Didn't take very long at all. Alternatively, if you like keyboard shortcuts, you can put your little cursor right at the start of the block of code here, and then use Command Enter or Control Enter, depending on your operating system, and that will execute the code. And so now I have an object named Texas Income. And if I click my Environment tab here, I can see that I have a data set with 254 observations and 5 variables. The variables in this case are referring to the columns, and the observations are referring to the rows. So I can click on this little entry here, and I see I now have a data set where I have a GeoID column, and that's going to be a unique identifier for every single county in the United States that uniquely identifies it among all other counties. I have a name column where, as you can see here, it's the name as you would commonly understand it. The variable, which is the unique ID code for, in this case, median household income. We'll chat a little bit more about that in a moment. And then the American Community Survey estimate from the most recent ACS data and the margin of error around that estimate. I can click any of these columns to sort them. So Presidio County has the lowest median household income of all 254 counties in Texas, around $29,000. And Rockwall County, which is east of Dallas, has the highest, and that's coming in nearly 125,000 is the median income. So that's regular ACS data. But we're interested in spatial data. And so to get spatial data, we add the magic argument geometry equals true. That's all you need to add. And you're going to get back pre-joined geographic information to the data that I just showed you. So let's go ahead and try that out. I'm going to go back to RStudio here, scroll down a little bit, and I'm going to create an object called Texas Income SF, SF standing for Simple Features, which is the data model used. So I'm going to go ahead and run that. And I can now take a look at my data. And you'll see the data are similar. They're the exact same data, in fact. If I sort it, you'll see the lowest value and the highest values are the same. But I have this extra column called geometry. That extra column, you can see some numbers here, stores what we call the feature geometry of the object. What does that mean? That refers to the shape that corresponds to, in this case, each county. So you can think about it this way. You have, for each row, a series of coordinate pairs, X and Y coordinates, like what you would plot on a map. If you played Children's Connect the Dots with all of those coordinates that are stored in this geometry column, you would get the shape of each respective county. What this means is we have a data set that we can go ahead and map. And you may or may not have noticed, we got that data set near instantaneously. It may have taken a little bit longer if yours wasn't pre-downloaded, but this whole process that would take hours for my students to learn, and even if you're experienced, is going to take you a little while to put together, can now be done in less than a second. Once we have that information in hand, we can map our data. So the simplest way to map your data is using the built-in plot function in R. And so I can take my income data and I can say which column I want to map. In this case, that's estimate. And I get a simple choropleth map of income in R. And so Jumping back here, I can go ahead and plot that. And here I have my plot. So you can see here the brighter yellow values, they tend to be located, if you know a little bit of Texas geography, they tend to be located in and around the suburbs of some of the major cities. So, here we have Dallas, Fort Worth, here we have Houston, and then here we have the kind of Austin, San Antonio corridor. That's where your highest incomes are going to be. Lowest incomes are going to be along the border in South Texas and in rural parts of East and Northwest Texas. So you get a little bit of a sense of that, but it's relatively straightforward to spin that up. And so moving beyond that, we already talked a little bit about looking under the hood, but just to reiterate, the SF corresponds to simple features, and the main GIS package for what we call vector spatial data, so points, lines, and polygons, is going to be the SFR package. It's phenomenally popular, and it allows for representation of geometries that we can think of just as discrete. And so a little bit of a GIS primer. We often work in GIS with either vector data, which we call discrete features. So those are things that you can specifically pinpoint on a map, like a specific location or a line that represents a road or a polygon, or you draw the boundary of a county. We can also work with something called raster data, which we're not covering today, and that is designed more for continuous phenomena, elevation, temperature, land use, that sort of thing. And so we have been able to pull that in. It looks a little something like this. And then you get this other information about the data set. So geometry type is multi-polygon. For a little bit of reference, polygon means enclosed shape. A multi-polygon means you can have multiple enclosed shapes that correspond to the same thing. So, think a county that has islands associated with it. Dimension of XY, referring to two-dimensional data. We have a bounding box. And then we're not really going to get into the weeds with coordinate reference systems, but it does give you that information as well. The static plot is interesting in and of itself, but if you're accustomed to working with spatial data in a GIS environment, you're used to having an interactive view that you can click around and get information from. And that's where the map view package comes in. The map view package is fantastic because it allows you to do quick interactive viewing of spatial data in R. And all you need to do is say map view. And then alternatively, if you want, you can specify a Z column, and that'll make one of those choropleth maps that you can explore. And so you get something that looks like this. I'm going to load in the map view package. And then I'm going to go ahead and run map view. And now I have an interactive map. I could probably use a little cleanup, but again, if I'm just exploring my data, I don't necessarily need to worry about that. I mentioned before that we see the brighter areas in the suburbs of the various large cities in Texas. I can zoom in and actually get that information, and I can click and get a little pop-up as well that tells me about it. So the highest median household income of any county in Texas is Rockwell County. I said it was east of Dallas, and indeed it is. It's geographically very small, and it's mostly suburban, but you can click and you can get this information about it. Collin County to the north is a larger county, also with a very high income. I can click around a little bit more. Here's Presidio County. I mentioned that's the county with the lowest median household income in Texas. That's way down here in sort of the rural border regions of far southwest Texas. And so having that interactivity is extraordinarily helpful. And we're going to be building on that over the course of today's workshop. And you're going to learn a lot of different ways to make interactive maps. All right. Just a couple quick questions as I'll pause. So Hillary, How do you search for variable names? That's what we're doing next. So bear with me. Chuck and Gay have questions about whether how do you know if you're using the ACS5 dataset or the ACS1 dataset? That is a good question. Let me show you just a little thing. And this is something that I give more information about in the first webinar, but I want to give a little bit of a primer about it here. So when I run this code, you'll notice I get this message that says getting data from the 2019 to 2023 5-year ACS. What that means is that the default data set pulled by getACS is the 5-year ACS. And if you want to look at the help documentation for getACS, enter a question mark into your console and then type getACS. And that will give you information about the function. And indeed, there are a lot of arguments that are what we call default arguments, so you don't need to put them in. You'll notice the survey argument, which defaults to ACS5. Now, ACS5 is the default, and that allows us to pull all of the counties in Texas. If I wanted to change this to the 1-year ACS, I would do survey equals ACS1. And now you'll notice if I run this, I get the message getting data from the 2023 1-year ACS. It does tell me, though, the 1-year ACS provides data for geographies with populations of 65,000 and greater. So what happens if I try to plot that data? I have a bunch of holes because many of the counties in rural Texas don't have populations of at least 65,000, and so they're going to be omitted. And so for spatial analysis, the ACS5 is likely going to be the data set that you want to work with. There are some workarounds that I can talk about, but if you want spatial coherence and spatial completeness, even though the ACS1 is more recent, you're probably going to want to go with the ACS5. And one other quick question: XY pairs. Should we always be assuming X is latitude and Y is longitude? So X is going to be the longitude and Y is going to be the latitude. That's the ordering. So not every service does the same ordering. Google does latitude first, longitude second. In R and in SF, it's longitude, latitude. So X, Y, it's in alphabetical order. All right, let's go ahead and jump back to the slides. Just got an example here. But let's talk a little bit about geography and variables in Tidy Census. So from a geography standpoint, there are a bunch of different geographies for which you can request data. The smallest geography at which data are available is going to be your census block, and that is only available in the decennial US Census. So using, say, get decennial. This central hierarchy or spine of this census diagram, those are going to be your main census geographies, and they all nest or fit neatly within one another. So census blocks fit within block groups, which fit within tracts, which fit within counties, et cetera, et cetera. You then have all of these other geographies that are used by the Census Bureau to tabulate information. You can get data at zip code tabulation areas, which are areas that approximate zip codes, or census places, or congressional districts. And so a question that arises then is, how do you figure out how to request that in Tidy Census? I have in the Tidy Census documentation a table that tells you how to put in different geographies for specific enumeration areas that you might want. A common question then that follows is, okay, that variable code you use for income, how do I find that out? The function load variables in Tidy Census is designed to help you with that. And so you can grab from all sorts of different data sets. We're going to be pulling primarily from the data profile today and the detailed tables. So if you want to pull in variables that you can browse, you can use this load variables command. And I'm going to show you how to do that here. I'm going to uncomment this real quick, and I'm going to make an object named vars that stores all of the variables in the detailed tables for the ACS. I'm going to click my environment button. You'll notice that there are 28,261 possible variable choices in the 2023 5-year ACS. That's a lot. So what we see here is a table that shows me 4 columns for the 5-year ACS. The name, that's going to be the ID code that you would put in as the variable when requesting data with GetACS. We then have a label that describes that variable and a concept that helps us understand the topic. So this first one is the total population in the sex by age concept. The geography column tells you the smallest geography in that main census hierarchy at which data are available. So these estimates are available down to the block group level. If we break them out by race ethnicity, they're only available then to the tract level. And so you can use this as a heuristic to help understand what data are available for a given table. And so you might say, well, this is great, but 28,000 variables, I don't have that kind of time. How do I search? Well, let's say we're looking for something like median household income. I have a search box here, and then I have a filter button here in this interactive data viewer in RStudio, which is very helpful for filtering down your data. So I can put in, let's say, income into the search box, and by typing in income, I've already taken down from 28,000 rows to just over 5,000. So I've thrown out a bunch of rows, but still there are 5,000 rows that have income somewhere. That's a lot. So I'm going to click this filter button now. And in the label column, I'm going to type median. This takes me down now to 124 entries. So I've gone with 2 queries from 28,000 to 124. And 124, that's something that I can readily browse through. And you'll notice there's still a lot of different breakouts for median incomes, but hopefully this allows you to, figure out how to filter your data down and choose the right variables for your project. All right. Let's jump back here and look at a couple other things. In many cases, when you're working with spatial data, you're going to be more interested in small area data. So you can go down to the block group level in the ACS and even the block level in the decennial census. And so census tract and census block group data require a state. So you have to put in a state to get that data. That said, you can also optionally put in one or more counties to get data for those counties. So you can request data that's basically filtered down beforehand. And so let's say I wanted to get income data by census tract, but I wanted to get it for all of the boroughs of New York City. So for those of you less familiar with US geography, New York City has 5 boroughs. Each of those boroughs is a county. These are the names of the various counties. So New York County is Manhattan, Kings County is Brooklyn, Queens County is Queens, Bronx County is the Bronx, and Richmond County is Staten Island. So I can request that data and pull it down. You notice I'm saying geography equals tract, and I'm specifying multiple counties here using the C operator. And then let's take a look at what I get back. So I'm going to grab my data. You'll notice that we do FIPS codes translations here. And I can run my map view command, and I get myself an interactive browsable map of income levels by neighborhood or census tract in New York City. So I can zoom in here to Manhattan, Upper East Side. We're going to have a variety of different census tracts with very high incomes. Down on the Lower East Side, we're going to have some lower income areas. So this allows you to do some of that more granular analysis. And again, you saw how fast it was for us to get the data. With respect to data structure, tidy census returns by default tidy data, so long form data. I got one query on social media. Someone had posted, "For the life of me, I can't understand why the default data format of tidy census isn't wide." And I kind of replied in jest, "Well, then I would have called it widey census." Let me talk a little bit about data structure and why I've made some of the design decisions that I have. So tidy data, the tidy data model has data basically stacked by row. We also call that long form data in data analysis, and that works really well with tidyverse wrangling functions. It's why I called the package tidy census, because I found myself reshaping my data to use it with the tidyverse all of the time. So you know what? I'm going to write this package and I'm going to do that by default. And so let's say you have multiple variables, and you'll notice here, if you supply what's called a named vector to variables, you'll replace the default census variable IDs with your own definitions. So here I'm pulling race for San Diego County, California, which is the county that contains the city of San Diego, and I'm getting it in long form. So let's run this through and take a look at it and see what that looks like. I run this through and I can take a peek at it by printing it out here, and I get what's called long form spatial data. So you'll notice that for each census tract, I have 4 rows. So census tract 32.12 has 4 rows. So I actually am repeating the geometries 4 times each, which if you're used to working with data from a typical desktop GIS style, that can feel a little bit uncomfortable. But as I think we'll show you, this allows for flexible querying and manipulation of data, and it works pretty well for some visualization functions that I'm going to show you a little bit later. But this is going to be our long form, so stacked census data. And granted, for many of you, you might say, well, that's not really the data format that I want. I'm much more interested in wide form data. And so the argument output equals wide, that's going to spread all your variables across the columns. And so you'll get 1 row per geographic unit, which if you're working in a traditional GIS sense is probably what you're most used to. And so let's go ahead and run that code. You'll notice this output equals wide argument is the key one. And we could try that out here. We're going to make this object called San Diego race wide. We pull that data down, and then we can take a quick look at it. And so you'll notice that by default for ACS data, tidy census and get ACS will always return both the estimate and the margin of error. So here we have Hispanic estimate, Hispanic margin of error, white estimate, white margin of error, et cetera, et cetera. But we only have 737 features as opposed to nearly 3,000. That's because in San Diego County, there are 737 census tracts. We have 1 row per census tract. And so you can pick and choose what you want to return depending on the nature of the project you're working on. All right. So moving through toward the end here of hour 1 before we break, I want to show you one additional workflow and talk a little bit about where the geometry comes from. And something we might actually have this spill over into hour 2 because we've been going for an hour, and I want to make sure that we get a break. So Tidy Census uses a package called Tigris internally to acquire census shapefiles. And so by default, it uses something called the cartographic boundary shapefiles, which are pre-clipped to the US shoreline. And what the last bit that I'll want to cover is, a problem that arises. And that's going to be something like your New York City income map. Even though we have data that is pre-clipped to the US shoreline, you're still going to see water areas included. And so if I go back here and I take a look at my viewer, you'll notice that the census tracts extend into the Hudson River and over into the East River. And so your normal crisp representation of Manhattan isn't going to be found by default because they're not in the shapefiles by default. And so over the years, I've written a variety of different utilities to offer solutions. And so the function erase water in the tidyverse package is really handy. What it does is it automates data pulls, and it pulls in water area shapefiles without you having to even fetch them out yourself. And then it performs a GIS erase operation to remove those areas depending on an area threshold. So the area threshold, which I'll show you, tells you, it basically allows you to specify how much water do you want to remove. So what I'm going to do here is I'm going to pull the data with the argument CB equals false, and this will help eliminate what we call sliver polygons in the overlay. I'm then going to run this erase water command. So let's go ahead and run that through. I am going to grab some New York City data, and I'm going to run this command. And area threshold equals 0.5. That means that we're keeping the 50% largest water areas. So you can think of it this way. If you rank all of the water areas that intersect New York City, the area threshold will say, I want to use the water areas that are above this threshold in size. So if I did 0.9, we would use the 10%, the largest 10% of water areas. In this case, I'm using the largest 50%. I run that through. I get the message that we're erasing the water area. It doesn't take that long. And so now, look at this. Here's my map of New York City with all the water areas included in the interior. It doesn't give me a crisp representation of Manhattan. But now, after I've erased the water, look at this. Once I zoom in, and you'll notice if it looks choppy when zoomed out, that's because map view does polygon simplification so that it can display its data rapidly. So if we zoom into Manhattan, look at how crisp of a representation we get. We even are cutting out lakes inside of Central Park. But we have here Roosevelt Island. You can easily see it. And we're appropriately representing the actual geography of Manhattan as we would typically expect it with respect to those rivers. All right, that actually ended up being perfect timing and took us right to the end of part one. So we're going to take a 10-minute break right now. I'm going to get up and stretch my legs a little bit. I've got some exercises for you if you would like, and I'm going to review the questions as well. So I'm going to go dark for a little bit, and I will see you back here. For those of you who are planning to attend the next hour, I'll see you back here in about 10 minutes. All right, welcome back, everyone. Hope you had an opportunity to stretch your legs, take a little break, and maybe work on the exercises if appropriate. I want to spend a little bit of time answering a few of the questions. And I'm not going to be able to get to all of them, but I do like to engage with a little bit of the Q&A as we go through this. And there are a ton of really good questions. So I've got a question about how to share interactive maps. I will be covering that a little bit. I'll make sure to spend some time talking about different ways that you can share your maps toward the end of this part two. And another question, is there a way to get the code of the states and the counties associated with that in a table format? So yes, you can. There's a built-in data set called FIPS underscore codes in Tidy Census that loads when you load the package. So if I type FIPS codes, you'll notice I have this data set built in. This has all of the counties that have ever been defined and their codes. So it's interesting. If I view the FIPS codes, I can browse this table, and you have the state and the state code and the state name, and then you have the county code and the county. And what's interesting about this, because some people have tried to use this as a data set that they want to work off of to do some work, I wouldn't necessarily recommend that. This is an internal tool that's used to do the lookup. And a reason for that, if we scroll down here to Connecticut, you'll notice that in Connecticut, we have way more counties than actually exist in Connecticut. So Connecticut, as of the 2022 American Community Survey, redrew all of their county equivalents because their counties in Connecticut are not meaningful geographic units from a political standpoint. They're just kind of historical legacy boundaries. So all of these counties weren't really meaningful to people in Connecticut. So the state decided to change to planning regions. And so whereas we used to have Middlesex County and New Haven County as an enumeration area for the census, now we have things like Naugatuck Valley and South Central Connecticut. These are the new ones. And so these old county codes correspond to pre-2022 data, whereas the new county codes correspond to 2022 and later. So this is just a lookup table that whenever you type in, okay, I want county equals Greater Bridgeport, it goes to this table, GetACS does, looks up what the appropriate county code is, replaces that in your query, and then sends the appropriate query to the Census API. So this is a handy data set, but I would just say be aware of how to use it appropriately, because you'll notice here Miami-Dade County and Dade County both exist in there. That reflects a renaming of the county. And it doesn't mean that those are separate jurisdictions because they're the exact same thing. Other questions. Can layers be added to help people make sense of the census tract map by having streets and highways showing? Absolutely. There are a couple different ways to do this. In the Tigris package, you can pull in road data and display that. Or alternatively, and I'll show you this, you can use something called a base map that I'm going to illustrate in just a moment that can show some of those features. Other questions? Is there a version of erase water that also accounts for parks or green spaces? No, because parks and green spaces are not found in the census shapefiles. So you would need to find that data set yourself. And then you wouldn't be able to use erase water with it, but you would be able to do GIS operations in R to do something similar. Another package or another question that I want to answer, and then we're going to move on. How much of a lag time is there in Tidy Census when the census releases new data, e.g. the 5-year ACS in December or PUMS data in January? Really depends. Typically with the ACS data, the package infrastructure is built such that it works immediately. So Census Bureau publishes the data and the data automatically work inside of Tidy Census, which is pretty great. With the PUMS data, occasionally there's some small changes that I need to deal with. Now, in particular, I have a process through which I need to pull down the new variable codes, rebuild the code book. And so it sometimes takes me a day or two to get that ready to go. Beyond that, the question was, should you install from CRAN? Should you install from GitHub? I tend to try to keep the GitHub version up to date. And then CRAN, I'll test it a little bit and then get those releases up there. It really depends on your organization, your level of comfort. Some organizations where your IT department locks you down a little bit more aren't able to install packages from GitHub. So I try to keep Tidy Census relatively up to date on CRAN, but you can't, you can only publish new updates to CRAN every couple weeks. They don't really like it when you do that more frequently. And so if you want to always have the most up-to-date version of the package with any bug fixes or new data sets, and you're comfortable with the GitHub version, then installing from GitHub is the way to go. All right. I do appreciate all of the questions. I can't, I'll keep some of those up and maybe get to them as we move through it. All right. Well, let's jump back here to the slides and dive into part two. A tour of map types with our mapgl and US Census data. So let's talk a little bit about mapping in R. And I did see one question earlier in the session talking about what are some various, packages that you can use and what are the advantages and disadvantages of those packages for mapping in R. And one of the great things about mapping in R is you have a ton of different options. Ton of options. R has been described, I didn't, coin this, but R has been described as the ultimate user interface. Because what you're doing in R isn't just about what R can do. Now, there are a lot of really great built-in statistical functions in R, but the beauty of R is its ability to serve as an interface to other technologies. For example, web technologies like JavaScript for interactive display of information, or connecting to databases, or wrapping C++ code that allows really fast compiled code to execute, and so on and so forth. R is really wonderful for that. And in many cases, when you're writing R code, you're not actually calling R under the hood. You're using R to talk to some other programming language that you don't necessarily even know how to write yourself. And so there are a ton of tools for cartographic visualization in R that, in my opinion, make it a suitable alternative to desktop GIS software in many cases. So ggplot2 is the most popular R package. It's been downloaded hundreds of millions of times, and it is arguably the premier data visualization library ever developed in any programming language. ggplot2 includes a lot of functionality for static mapping. I use it quite a lot. CMap, which stands for thematic map, is another great package for mapping, and you can do both static and interactive maps with it. MapSF is another one. For interactive maps, there's Leaflet and MapDeck and RDeck. There are a lot of different options. And so you might say, well, there are already a ton of options for making maps in R. Why did I go and write another R package to do mapping in 2024? It's a great question. Frankly, when it comes to, open source software development and, building out some of these tools, I think a lot about tools that I really like and that I use and that I would like to be able to fit within my own workflows. So I use R for 95% of my work. It connects with everything that I need. It does just about everything that I need. That said, I really like the Mapbox and MapLibra libraries for cartographic visualization on the web. And there wasn't a MapLibra library that existed that had all of the features that I wanted. And there was a Mapbox library, but it didn't support the later versions of Mapbox GLJS, the Mapbox JavaScript library. Uh, and so it didn't get a whole lot of features that I really wanted in my own projects. And so I decided to write it myself. And I spent much of the summer of 2024 building out this package, and I've been updating it and maintaining it since then. It's called MapGL, and I want to show you how it works. I hope you like it. It is an interface to the Mapbox GLJS and MapLibra GLJS libraries. And so it allows you to use WebGL in your browser for really high performance web mapping. You can map a ton of data in your browser, and the maps are really fast and, frankly, a lot of fun to play around with. Now, one thing about just a little bit of background. So Mapbox GLJS was the main library that was released by the company Mapbox. And prior to version 2 of the library, the license for Mapbox GLJS was open source. And open source, just for reference, for those of you who aren't as familiar with the terminology in software, open source means the source code is publicly available typically, and it can be copied and used in other software. There are all sorts of different open source licenses, but it's a much more permissive model, kind of a community maintained model. Now, Mapbox had noticed, and I do understand this, that GLJS was potentially being brought in and used to power mapping libraries by much larger companies, and so they decided with version 2 to adopt a commercial license. So to use Mapbox GLJS, which arguably is the premier mapping library out there nowadays, you do need to have a Mapbox account, put in a credit card, and use an access token. And so this was a very big deal when this happened. It was around, I think, 2020 that they decided to do this. And there were a lot of people in the mapping community who weren't happy about this decision. I again am a big proponent of open source software, but I also understand the need of companies to make money and pay their employees. And so, this was where Mapbox found itself. And so Mapbox since then has been releasing GLJS as a paid product. MapGL gives you access to Mapbox GLJS, assuming that you have a Mapbox account and an access token. MapLibra is a community fork of Mapbox GLJS. So basically, a group of developers took the open source version of Mapbox, given that its licensing at the time permitted it for version 1 and has continued to maintain it as open source software that is free to use. MapGL, I quite like Mapbox products, and Mapbox GLJS is fantastic. MapGL supports that paid product, but it also supports the free MapLibra product because I know that not everyone is interested in the paid version. So today we're going to be using MapLibra, so you don't need to worry about setting up a Mapbox account. So if you are a Mapbox user, I would strongly encourage you to check out the MapGL documentation, as there's a whole lot that you can do with that. And in fact, I'm going to give you a link right now to the MapGL documentation and talk you through just very briefly. So I'm putting that into the chat. MapGL can do a ton of stuff. And we're going to be scratching the surface today, but this is what your documentation is going to look like. Use today as a jumping off point. We're going to learn a little bit around getting started using layers. For those of you who are more advanced, you can build out dashboards with Shiny using MapGL, and even story maps, which is the newest feature in MapGL, which I have a ton of fun with. And maybe I could show that to you a little bit later in the workshop if we have time. So with that in mind, let's go ahead and get started. And we can use MapLibra without an account or an API key. So let's do a very quick introduction to MapGL. So just to show you very briefly, when we call, we'll load in MapGL with the library mapgl command. And then to make a MapLibra map, all you have to say is just MapLibra. And I'm going to show you how that works here. I'm going to jump back over to my map and code. I'm going to load this in. And then here I have my interactive MapLibra map. And so the default style used, so that's going to be your base map, is one of Carto's open source styles, the Voyager style. And this is generally a good base map for thematic mapping. So I could zoom in. This isn't typically going to be a street map that this isn't typically going to be a street map, though you are going to have roads in there as you zoom in. You're not necessarily going to have all the labels unless you zoom in pretty far. But this is a free product to use. And so at the end of the day, kind of you have a basic kind of Google Maps style interface. You'll notice using that default Mercator projection. And that's going to be your default in MapLibra. Takes one line of code to get your interactive map like this. And you can think of this as the template. Well, this is a canvas upon which we'll paint with our data. So as of version 5 of MapLibra, one of the main reasons I actually wrote mapgl was I really wanted a globe projection for my maps. I just had a lot of trouble using Mercator for international mapping, just because, again, if you look at it in a Mercator projection, it's the Greenland problem, right? So here's the island of Greenland, or as has been proposed recently in US Congress, red, white, and blue land. It's Greenland is a territory of Denmark, and the Greenland problem in mapping is a pretty important one when we think about distortion in web maps. So Greenland is this big island in the Arctic and is a territory of Denmark, and appears really, really large in a Mercator projection. If you go and look at an actual globe, though, here is what Greenland actually looks like. So in the Mercator projection, Greenland and Africa appear to be around the same size, when in reality, Greenland is 1/14th the size of Africa. And we could get into the weeds with map projections. Basically, the Mercator projection was designed by a Belgian cartographer named Gerardus Mercator to primarily be used in navigation. And so lines of constant course on the map are represented as straight lines. So it was a good map for navigation, not necessarily the best map for showing international differences, as it grossly distorts features toward the poles. So you might say, well, why would this be a standard in web mapping if we know the problems with Mercator? Well, most web maps aren't zoomed out like this. Most of the time when we're, say, using Google Maps, here I'm going to zoom into my city of Fort Worth, we're zoomed in all the way here, and we're trying to figure out, well, how do I get from here down here? And so I'm not worried about distortion in Greenland if I'm just navigating around my city. And in that case, the conformal properties of Mercator end up being a big advantage. So what I really liked about Mapbox is, and the default in Mapbox create adopted a globe projection. They were an early adopter of this. The most recent version of MapLibra, which is included in the latest release of mapgl, offers a globe projection as well. And so if you use this function set projection globe, and I want to talk a little bit about what I'm highlighting here too. This is the pipe operator in R. It's going to be your pipe and then your caret. And basically you can think of this as start with MapLibra, then set the projection to globe. So if I run that, you'll notice I now have an interactive globe. And the cool thing about it is it transitions as you zoom in to Mercator, because Mercator is a great projection when zoomed in. Again, because it preserves directions pretty well. Like north is up, east is to the right, south is down, and west is to the left. And so that is really helpful when you're zoomed in on a city. When you're zoomed out, though, it adjusts back to a globe. And so now I have this nice interactive globe in basically a couple lines of code in R, which is a lot of fun to play around with. I see one question, could not find function set projection. Make sure you install the latest release of mapgl. So if you have an older version of mapgl on your computer, make sure you install the latest release to get set projection, because this is a fairly new feature in the package. All right. So moving along here, and I'm getting some great questions. One person's asking, how do I zoom in or zoom out? I'll show you something here. I'm using the scroll wheel on my mouse. If you don't have a scroll wheel, something that you can add is a navigation control. And so if I do add navigation control and I run that, it'll add a little navigation control for me that allows me to have these zoom in and zoom out buttons. So I'm using the scroll wheel here. If you're on a mobile device, or you can, you can pinch and use your fingers to do it too. But that navigation control doesn't show up by default, but you can add it with add navigation control. All right, so this is kind of fun to play around with, but our purpose today is mapping census data. So let's talk a little bit how to do that. In Mapbox and MapLibra, we add data to our maps as what's called a source, and then we style that source as a layer. And what I've tried to do with MapLibra, and you'll get a sense of this in Mapbox with mapgl, the JavaScript libraries are extraordinarily powerful, very powerful, but they're also fairly verbose. So if you go to the documentation for either of the libraries online, you will see that in many cases it takes a lot of code, a lot of JavaScript to create a map that you might be accustomed to creating with less code in R. And so as a developer, this raised a dilemma for me. On the one hand, you can build in a whole lot of functionality just to automate away a lot of the process of building the maps and try to make it easier for the user. On the other hand, anytime you abstract like that, you take away some of the richness of the underlying library, which is quite expressive and allows you to do a whole lot of customization. I tried my best to find a middle ground. So if you're accustomed to using some of the other R mapping packages, you may find that mapgl requires a little bit more code than you would need for those other mapping packages. But it does allow you to create custom visualizations that are pretty expressive and exposes a lot of that kind of richness to you on the R side. So let's make a very basic visualization that doesn't really work very well, but just to illustrate how the defaults work in MapLibra. So to display a polygon layer, so census tracts, for example, we can display that as a fill layer. We call that a fill layer in Mapbox or MapLibra, and we use the function add fill layer. So we're going to grab some data on median age in Phoenix to illustrate this. So I'm going to fetch this data here using get ACS at the tract level for Maricopa County, Arizona, from the most recent ACS. And this is the code for median age, which in the Phoenix area is a great variable to map because you have a number of retirement communities in the area. So let's grab that data. And I've pulled the data down, and now I can make a map of it with my MapLibra code. And it's going to end up looking something like this. I've tried to keep the size of the HTML file smaller, so I haven't embedded all the interactive maps. Some have just screenshots. Not a great map, but let me show you what that looks like interactively. So here's the code that I'm using. I'm calling MapLibra, and I'm specifying a bounds argument. This sets the initial bounds of the map. Some mapping packages inherit this. Leaflet does that in R from the data object that you're mapping. I didn't really want to do that because there are all these cool animated transitions that you can have when you don't do that. But you can specify the bounds. And this is one of the little tricks that I've included in there. Instead of having to specify the bounds as the actual bounding box of coordinates, mapgl will figure that out from our data object. We can also supply a data object directly as the source inside add fill layer, and then every layer has to have an ID. And I require you to manually put in the ID because knowing that ID I find helpful, for a variety of other purposes. And so we go ahead and run that through, and you get a map that looks like this. It's just black. Now, black is the default style for fill layers in Mapbox and MapLibra. You can't see any of the borders. This isn't and the census tracts are fully opaque. So this isn't a very useful map by default, but you can think of this as the starting point upon which we can start to do some styling. So let's talk a little bit about styling. So map view is going to be your simplest way to make a choropleth map. And so we're going to talk first about choropleth maps. So choropleth maps are going to be maps that use color or shading to display differences in some attribute of interest that you're trying to map. In this case, it might be median age. And so in some mapping packages, they try to abstract this away a little bit and make it easier. For example, map view is the easiest. You just say zcol and equals whatever your column is, and it makes that map for you. That is fantastic to have that functionality, but that functionality is occupied by map view. And we're in, I think, very early discussions to potentially integrate mapgl into map view, which would be quite exciting if we get that done. Building out visualizations requires a little bit more code, but you can create just about anything that you want on the fly by doing this. So for a continuous choropleth map, where we basically map a continuous color palette to our statistical data, you'll use in these libraries an interpolate expression. What that does is interpolates between colors along a series of values. So the corresponding R function that I've written is called interpolate. And so in this case, I specify the ID in the source, and I set the fill color property to an interpolate expression where we're targeting values in the estimate column. The values are going to range. So the low end of my range is going to be 4, which is the lowest median age in Maricopa County, and the highest is 77. So we're interpolating between those values, and we're mapping based on these stops. So we're mapping from light blue to dark blue. We set an NA color of light gray because the default black, in my opinion, is very distracting. I don't want people's attention to be drawn to the areas that don't have data available. And then I can set the fill opacity to 0.7, which makes my census tracts semi-transparent. So let's go ahead and try running this through. This is now I've gone from black census tracts where you can't see anything to a map where I can actually see some patterns. So in this particular case, and you might say, well, I need a legend. I need more information. We're going to get to that. But in this case, you can see how we have painted with our data. We're interpolating light blue to dark blue between these values. And so the darker blue areas, those are going to be areas with higher median ages. And you can see that there are these retirement communities in Northwest Phoenix that have presumably very high values. The lighter areas, those are going to be areas with lower median ages. And so, in this particular case, that gives you some, some basic information about how to get this set up. And I noticed Declan asked a very good question. To avoid hard coding the range for values, can we use min and max functions within the add fill layer specification? Absolutely. And that is a great way to do it, to avoid hard coding if we're going in and pulling in different pieces of information that we want to map. But what's fun about this, and part of the reason I like exposing the underlying interface, even though it requires a little bit more code, is I can now create any color palette I want, and I can map it to data values however I want. So let's say I wanted to redo this map, but I wanted to do a color palette that interpolates between magenta and cyan. I'm not necessarily recommending that from a data visualization standpoint, but take a look at this. I can do that, and it literally does that on the fly for me. any custom color palette you can build on the fly using Mapbox and MapLibre in this package. And so functionally, you can create any kind of map that you want once you get the hang of the interface. All right, so that gives you a little bit of information about how to do a continuous choropleth. Um, you might also be interested in creating what's called a classed choropleth. And this is something that's going to be very familiar to those of you from a GIS background. You want to put values into buckets and then visualize those buckets. This requires in the JavaScript library something called a step expression, which kind of feels a little unfamiliar to our users, but I'll go ahead and walk you through it. I'm going to grab some colors here using the Viridis Light package, and I'm going to use those 5 colors for my various buckets. So we're going to grab these colors, and I can take a look at my colors, which I'm storing in this object called colors, and I get these hexadecimal codes. And so hexadecimal codes are 6-digit letters and numbers codes that uniquely identify a specific color that can be used in data visualization or on the web. And this can be interpreted by mapgl. So talking through this a little bit more, how we get this done. A step expression in MapLibre requires a little bit of different setup. So we have a base color and then we have stops that are mapped to bin edges. And so in this particular case, I've replaced the interpolate expression with a step expression. I'm saying, okay, I want to map on the estimate column. That's my median age. My base color is going to be the first color. That's going to be everything below the first value. So in this case, it's going to be 0 to 25. My stops are going to be the second through the fifth. And so 0 to 25 is going to be my base color. 25 to 40 is going to be my second color. 40 to 55 is my third color. 55 to 70 is my fourth color. And then 70 and up, everything above the last value, that's going to be my fifth color. That's how step expressions are specified in the underlying JavaScript. And so I wanted to bring that functionality and that flexibility to R. So once we do that, we'll go ahead and initialize the class choropleth and display it. And it's going to look like this. Now I'm only displaying 5 colors on the map. And you'll notice because I defined these breaks manually, there are going to be a few colors that aren't as well represented. So under 25 is pretty rare to have a median age under 25. Those are going to be very, very young areas, or in many cases, they're going to be in and around universities. So this is the area around Arizona State University. You'll see median ages under 25 there. Those retirement communities up here around Surprise and Sun City West and Sun City, those are going to have those median ages above 70. And I saw a great question from Heidi. Well, how do you add a legend? I'll show you. I'll show you right now. It's one thing to have these maps. You're probably going to want a legend to show what the various breaks mean. And the add legend function allows you to add either categorical or continuous legends. So both are supported, and you can build them fairly manually from the ground up. So I'll supply a legend title. I'll supply the values that I want to show, the colors that I want to show. And in this particular case, I'm saying I want to do a categorical legend. If I had chosen a continuous legend, what it would do is it would interpolate a color ramp amongst all those colors and then stick these values at the appropriate locations along that color ramp. But in this case, we're doing a classed choropleth. So we want a categorical legend with little legend swatches for the different colors. So going back to R, we're going to go ahead and add the legend. And we see here we have our legend. So the dark purple, that's going to be under 25, the all the way up to 70 and up. And you'll notice I've tried the legends, thought about whether or not I should have a functionality for automated legends, and I decided not to do that, in part because I like allowing users to be creative with how they put their legends together. And so this does put the onus on the user a little bit more to set things up, but it doesn't lock you in to predetermined legends uh, in the way that maybe some other mapping packages do. And that's not a criticism of other mapping packages. It's just um, I'd like users having that degree of flexibility. So here we have, an example map with a legend. That's pretty interesting. I can do some exploration. But a common thing that you'll want to do with interactive maps is, well, interact with them. As of right now, I can't click on anything to get any information, and I don't have any styling or hover effects that really allow the user to feel like they're fully interacting with it. And so let me show you how to do that. Add some effects. In this particular case, I'm going to show you a couple modifications. I can specify a column I want to put in a tooltip, and that will create a hover tooltip that every time I hover over a particular location, I will get the value in the estimate column. And I can also specify hover options. I do that as a named list where you can say, when you hover over a feature, what are the properties you want to override and how do you want to override them? So in this particular case, I'm saying, okay, when you hover over a given location, change the opacity to 1 and change the fill color to red. So let's see how that works. Okay, I've taken away the legend in this particular case to simply be able to show everything. But watch what happens when I move my cursor. You'll notice I move my cursor over a given census tract. It highlights it in red because that's what I told it to do, and it shows the underlying data value. So up here, you can see these census tracts with median ages above, in some cases, 76. I can go down here to the Tempe area, and you can see what those median ages are. This one here, which is right around ASU, that's going to be 19.1, and some of these other neighborhoods around it are also under 25. So, basically, I'm getting some great questions. I'm going to address some of those as we get towards the end. But I love all of these questions that people are thinking around. All right, so I want to spend the last 10 minutes talking through some alternative map types because choropleth maps aren't necessarily well suited for certain types of data. They're not great for count data in particular because your focus is on the area, and larger areas can have larger baseline populations. And so if you want to show variations of count data, sometimes it helps to have a standardized shape that you visualize. And an example of this is something called a graduated symbol map. And so we're going to go ahead and grab some data in a structure that we looked at earlier in the workshop on race ethnicity in San Diego, California, and consider some alternative map types. So jumping back here, we're going to make sure that we have that data. And we're going to create something called a graduated symbol map. And so the nice thing about graduated symbol maps, especially for making comparisons, is they use the same shape for all locations. Whereas choropleth maps are going to be tied to the shape of the actual polygon. And sometimes you have really big polygons, sometimes you have small ones. And in turn, making direct comparisons can sometimes be a little tricky because you're not doing one-to-one visual comparisons. So graduated symbol maps are often better for count data than choropleths, again, because the shapes are directly comparable. In mapgl, we can use something called a circle layer rather than a fill layer to visualize data as graduated symbols. So the first thing that we want to do is convert our data to what we call centroids. So we're basically going to plot a point at the center of each census tract polygon, and then we will visualize those points. And the st centroid function in the SFR package, that GIS package I mentioned, is how we're going to get that done. So let me show you briefly what that looks like. I'm going to filter down my data for only those rows where the variable is Hispanic, and then I'm going to make my centers. And I functionally converted my census tracts here to, instead of polygons, I've converted them to points. From there, we can use a circle layer to create a graduated symbol map. And you'll notice here that there's a little bit of different code. So circle layers have different properties. They have a circle radius. And what I'm ultimately doing is, I'm going to jump back here to the script. What I'm ultimately doing is I'm setting different values. And so you'll notice here, I'm setting breaks at 500, 1,000, 1,500, and 2,500. We can kind of see what those, where these different values are going to fall into those buckets. I'm setting a base size of 2, and then I'm doing a sequence from 4 to 10 of other stops for my circles. I can set a circle opacity and a circle color, and I run this map through, and you'll notice here, I have my graduated symbol map. And so what we can see as we zoom in, it gets a little bit clustered up when we're zoomed out. But as we zoom in, you can see some of those variations. So the northern parts of San Diego, there are going to be some areas with relatively small Hispanic populations, but through National City, Chula Vista, you're going to have larger populations. And that allows a different kind of visualization where my shapes are no longer tied to the census tract shapes, but they're shown in an alternative way. And you have this cool overlapping effect because we've modified the transparency. We can add a legend in a similar way where we specify this argument circular patches equals true. And so if I go ahead and run that, I get a graduated circle legend that maps to the actual sizes of these circles. And you can kind of compare them here. That this circle here, which is in 2,500 and up, it's going to match the size on the legend. So I find that pretty helpful for communication purposes. All right, so that's graduated symbol maps. I want to show you another map type I quite like, which is called the dot density map. So we've shown choropleth maps, we've shown our graduated symbol maps, but what if we want to actually show heterogeneity? So where different groups live together. That can be quite difficult to do. Typically, thematic maps are good at showing one thing at a time. So dot density maps are a lot of fun. They scatter dots proportionally to data size. And then they allow for mixing of the dots. And you can color the dots by category to show within, say, census tract heterogeneity. Traditionally, dot density maps have been slow to make in R, but the function in tidy census as dot density leverages some newer R packages, and particularly the terra R package, to get this done. Now, terra isn't installed by default because it's a big package. So to run this code, you will need that terra package installed. So first things first, we're going to run this as.density function. And we're basically saying, take our race data. We're going to use the estimate column as the value. And we want to look at those values and create a dot for every 200 of that value. And then we want to classify those by group. And the group is found in the variable column. And so Zeke's question about the filter, you'll need, in this particular case, I'll put it in the chat, run library tidyverse, and that will allow you to run that code correctly. So generating the dots and just showing you what that looks like with as.density, it doesn't take too long to generate the dots, just typically a few seconds. And now we can look at it. We have a whole bunch of dots. In fact, we have 15,000 of them. And then they're characterized by their variable. It does retain the census tract that they belong to and the parent estimate and the parent margin of error, though that's not as relevant here. And so in this particular case, these dots are all scattered and randomized within their census tracts. And what that allows us to do is generate a dot density map. And we can do that with a circle layer. And I want to show you a couple different ways that you can do that. So first things first, we're going to use a new expression. So there's interpolate expressions for continuous data, step expressions for categorical, or I should say stepped data. And then for qualitative data or categorical data, where there's no ordering or ranking, you're going to use something called a match expression. And so in this particular case, we're matching different colors to different groups. And so I can run this code and make an interactive dot density map. So now I have an interactive dot density map of race ethnicity that's zoomable. It's super fast for San Diego. Beyond that, you might be interested in making a couple modifications. I want to show you something that really exposes some of the power of this library. I can create zoom dependent styling as well, where I interpolate the circle radius by zoom level. I can move the labels. You see how the labels are obscured by the dots? I can move them in front. And I can add a legend. And so in this particular case, I run this through. And you can see here now how those city labels have now been brought to the front. I have a legend here. I make this just a little bit bigger. And watch this. When I'm zoomed out, the dots are smaller. As I zoom in, notice that my dots are getting bigger. And you can fiddle around with this to try to get the right visual representation. But if the goal is to be able to show appropriate heterogeneity at all zoom levels, in this particular case, the radius size is always 2 pixels. And so if I zoom in, 2 pixels ends up being really small. If I zoom out, everything is kind of mashed together. Whereas if I'm interpolating the zooms, I'm now using a very small pixel size, 1. I zoom in, and now my dots get bigger, ideally giving me a nice representation at all zoom levels. So getting a little bit of a sense of how powerful this library is. All right, that's the end of part 2, right on time. So I've got a lot of great questions that I'm going to try to answer at the beginning of hour 3. We're going to take a 10-minute break. Try reproducing one of these maps with a different state or county combination and play around with mapgl and mapgl a little bit. So I'm going to go dark for 10 minutes. I'll be back at about 2:10 Eastern Time US, and look forward to showing you some more advanced features and workflows that you might be interested in. All right, I'll see you in a bit. Okay, welcome back, everyone. And many thanks to those of you who have stuck around for hour 3. We have had such an amazing turnout for these workshops. In a few years ago, by the 3rd workshop, we would have under 100 people still around for hour 3. Now there are 268 of you still here. We've had well over 1,000 of you register for these workshops, and I fully understand that this is a big time commitment for all of you. You all are very busy, have very important things to do, and the fact that you're spending this time with me, that really means a lot. So I do appreciate it. I want to spend a few minutes before we dive into part three. And part three is going to be some advanced workflows that I think we'll have some fun with. I want to spend some time talking through a few of the questions. So, one question is mapgl available on CRAN or on GitHub? It's both. You can install from CRAN. I try to keep that reasonably up to date. Um, Another question, and I kind of glossed over this one. Where do you find Color Brewer 2 library color codes? We're using Color Brewer here in this map, and I'm pulling that using this brewer.pal function and the R Color Brewer package. So Color Brewer is a pretty fantastic resource for color, for cartography, and other types of data visualization. And that is the way that you can access those colors and generate those color palettes in R. A bunch of other really good questions. Can you add a north arrow and scale bars? So I don't have functionality for a north arrow, but scale bars are available. Let me show you how. For any of these maps, like let's say we have this map here, a scale bar can be added. I'm gonna go here with the add scale control function. And so you can decide if you want it to be metric or imperial units. You can decide what you want the max width to be. You can decide on the position. It defaults to the bottom left of your map. So I'm just going to do it with the defaults here. And I'm going to rerun this, having added a scale bar control. And so this is what your default scale bar control looks like. And you'll notice if I zoom out, it changes. If I zoom in, it changes. So we can kind of go in here. It's about 2 kilometers. It's about, 300 meters, that sort of thing. And so that gives you a little bit of a sense of how you can add features. So there are a whole lot of map element features in mapgl, where you can add a draw control, you can add a full screen control, a geocoder, a geolocate feature, a little globe mini map. There is a ton of stuff that you can add, a reset control. I'm not going to go through all of that, but I've tried to, bring in a bunch of different features that you can add on to your maps to, try to make them as functional and informative as possible. Let's see here. Is it possible to make a hex bin map? So we just added functionality to do that. I don't really have time to get into it live, but we do have support for H3 hexagon data, and you could always bring in your own hexagons and visualize them as a fill layer as well. The last thing, and a couple people asked these questions, is a couple people asked questions on, why would you use mapgl over mapview or leaflet? That's a great question. MapLibra and mapbox.gl.js represent the state of the art in web mapping. They are the most powerful and most flexible web mapping libraries around. Even the person who created Leaflet would tell you as much. He's one of the lead developers on mapbox.gl.js as well. So Leaflet is a raster-based map, whereas Mapbox and MapLibra are vector-based. And what that means is that Mapbox and MapLibra allow for much smoother and dynamic data display, and you can do a whole lot more with the maps, as opposed to a leaflet, which is much more limited. So you can display more data with MapGL. You can style your data on the fly in ways that you can't really do in leaflet. And leaflet simply represents older technology. That said, the Leaflet R package is phenomenal. It's been actively maintained for 10 years. Leaflet is probably the most popular mapping library in the world. And if you're using Leaflet and it's working well for you, I would encourage you to continue to do that. I personally found, and this is kind of my philosophy around open source development, I write these packages for me. This is something where you're providing a service to the community. I'm not really so concerned about, oh, is this going to be downloaded a million times? I write the packages to solve a problem that I have, and I really wanted to have these platforms available in the work that I do. And then I make them available to the community, and hopefully there will be some uptake, and fortunately there has been some. So, at the end of the day, you find the best for your use case. I think mapgl is a great option if you want to do really customizable and performant web mapping. If you're looking for quick mapping, MapView is the way to go. If you're looking for the library that has the biggest repository of examples out there, that's going to be Leaflet. So it really depends on the use case. Um, yeah, so I've got one other question that I that's been asked, and how do you share these maps with others? Um, there are a variety of different ways to do that. One thing you can do if you want, there's a service that Posit offers called rpubs. You can publish the HTML directly from here to do that. Each of these maps are what's called an HTML widget. And the HTML widgets package, which was first developed 10 plus years ago, is a bridge package between JavaScript libraries and R. And mapgl uses HTML widgets under the hood to allow you to interact with JavaScript from R. And so if I have an object here, density map2, I could do something like library HTML widgets, and then I could do saveWidget density map2, and then I could call it something like density map.html. I'm going to save it in my mapping subfolder and run that through. And what it's going to do is it's going to write that map to a HTML file. So here I have an HTML file, and I can open that in a web browser. And I'm going to bring that over here. I'm going to zoom in just a little bit. And now I have this density map. Let me expand that up a little bit. That is available as a standalone HTML file. And I can use that HTML file and embed it in a website. So, those are just some things that that are available for you to do. So I'm going to kind of post that for you here in the chat. So that's some example code that would allow you basically in saveWidget, you need to specify the name of the map that you've given it in terms of an object in your R environment, and then the output path to an HTML file you want to save to. And then you can embed that as an iframe, or stick it in on your web server and show it that way. So let's dive in now to part 3. We've got about 40 minutes left. And I have a couple examples to show you that I think will be pretty fun. Now, a couple of these examples might tax your computer a little bit, so bear with me. But they are use cases that do come up. And I think they illustrate some of the power of working with mapgl accordingly. All right, so let's take a look at some advanced workflows, national mapping, and small area time series analysis. All right, first things first, we're going to talk about national mapping for the United States. So this is a huge challenge that comes up when you're trying to map the entirety of the US. The US is non-contiguous. We have the continental United States, 48 states plus the District of Columbia. And then you have a couple other states that are fairly distant from the rest of the country. Plus, then you have territories like Puerto Rico, which are typically treated as a state on these sorts of maps. And so this creates some problems because you can't, well, you can just make maps that show the states where they are. But Hawaii in particular is pretty far from the continental US. And so you're going to need to have a fairly zoomed out view, which doesn't necessarily give you the detail that you want. This is a problem that comes up again and again. Beyond that, the default Mercator projection used in web maps, it grossly inflates Alaska's size. Alaska is very large, but it appears even larger on a Mercator map. It has that Greenland problem, right? Because it overlaps the Arctic Circle. And so that is not ideal either. And then visual comparisons in turn get difficult because, I want to compare the different states. Alaska's way over here, Hawaii's way over here. That gets tough. So let me show you a basic example. We're going to plot median home value from the 2023 one-year ACS by state. So I'm going to pull down median home value data by state. I'm going to go ahead and make a basic map here. So let's run that through. And this is going to be my first US map of median home values. I'm interpolating between like a blue and a green color here. This is the default. And so frankly, we mentioned kind of why would you use my package over a leaflet? So leaflet only supports Mercator projections. And so this is kind of what you're stuck with. You can see here how big Alaska looks. Alaska is really big, but it's not this big. Hawaii's way out here. Puerto Rico's way over here. I can zoom in to the continental US, but now I can barely see Puerto Rico, but I can't see Hawaii and Alaska. So I need to zoom back out. And now I can barely see detail in the Northeast. And frankly, just representing our information like this is not an ideal way to do it. We want to be able to actually make comparisons because, frankly, if you look at it, Hawaii has some of the highest median home values in the country. And we're, you know, basically, if we're focusing in on the rest of the US, Hawaii is way off of the map. So if this is our highest data point, we can even take a look at our data and just investigate this a little bit. Hawaii ranks #1 for median home values. So by far, do we really want to leave it off the map? No. But if we're using the default Mercator projection, we're kind of resigned to doing that. So let's take a look at some alternatives. Maybe we could use the globe projection. So MapLibra supports a globe projection. Mapbox, which we're not discussing today in great detail, supports a whole bunch of other projections as well. So we might use a different map projection. Let's use the globe. What about a globe projection? This could make things a little bit better. So we're using set projection globe to set that globe projection. So let's give that a try. For one, the default isn't amazing, in part because the Aleutian Islands stretch all the way over here. So I'm going to go back down. I'm going to zoom in a little bit. And this is better because Alaska is now more appropriately sized. This is how big Alaska actually is as compared to that Mercator representation, which was a lot bigger. But it's still not amazing because, for one, I zoom in here to the US, Hawaii is still way off of the map. I can get a view where I kind of see everything, but that distorts the shape of Hawaii over here. It distorts Alaska. Frankly, it distorts just about everything. I want to be able to have a view where the continental US looks about like what I'm showing here, but I can also see Alaska, Hawaii, and Puerto Rico. That's what I want. And commonly, what you'll see in mapping is what we call shifted geometry, where you'll move Puerto Rico, you'll move Alaska and shrink it, you'll move Hawaii and then blow it up a little bit, and you'll move it to a different location on the map so that it is closer to the continental US. And then you put an inset around it, possibly, or you just sort of understand that we know Alaska isn't where we've moved it to, but we just want to be able to see it. Because at the end of the day, if you're looking at a map like this, you're interested in the colors of the states. You're not so interested in having perfect geographical accuracy. So let's talk a little bit about how we get that done. In the tidyverse package, there is a function called shift geometry that allows you to shift and optionally rescale the non-contiguous parts of the United States. So I wrote this a few years ago. I remember I had a colleague here at TCU who, I think popped in my office and said, I'm trying to make a map for this project I'm working on, but it's very difficult to move Alaska and Hawaii. How do I do that? And so I thought, well, you know what? This is a solvable problem where instead of having to do this by hand, ideally, you'll have a function that just does it for you. And what it does is it identifies any features that are in Alaska, Hawaii, or Puerto Rico, breaks apart a data set accordingly, moves the features that need to be moved, and then reassembles it for you. So let me show you how this works. I'm going to shift my data, and that is going to move Alaska and Hawaii. So if I print out my US value shifted object here, you'll notice it's still the same data, but I'm doing a different projected coordinate reference system. And so my coordinates are going to look a little bit different, but where Hawaii, Puerto Rico, and Alaska are located is no longer actually where they're located. I've moved them. So let me show you how this works. I'm going to recreate my map that I just created with the globe projection, but instead I'm going to use my shifted data instead of the original data that I had. So let me give this a shot. It's not what I want. This is now what I get. All right, I'm actually getting there. Here I have the continental US, I have Alaska, I have Hawaii, and I have Puerto Rico. And they're all visible relative to each other. What's the problem? It's still not perfect. Why? Well, for one, Hawaii is not in Mexico. We have the base map here, which the base map is helpful. It's nice to have the base map, but we know that Alaska is not sitting here over Baja California. Hawaii is not in Mexico, and Puerto Rico is not in the Gulf of Mexico. And so, like, we understand that. Um, and we're fine with that typically if there is no background. But given that we have an interactive map and a background, that can get confusing. So there's still probably some modifications that we need to make. So there's a couple different ways that we can deal with this. This the general solution is let's just get rid of the base map. Because frankly, if we have a US map and we're assuming an audience that understands basic US geography, the base map isn't necessary. And there's some other things that we can do to fix that. So the solution is to remove the base map. And this actually answers one of the questions that someone had asked earlier. So if you're using Mapbox, one approach is you can create a blank style in Mapbox Studio and bring that in as the style you're using in your map. So we're not covering Mapbox because of the paid account and access token issue. for the purposes of today's workshop. But if you are using Mapbox, Mapbox is a really cool tool called Mapbox Studio. And what Mapbox Studio allows you to do is take a base map and style it, any element of it. And just to give you a little bit of a sense of how that works, if I had been calling, say, a default Mapbox map, I could take a Mapbox map like this. The mapbox.gl function, if you have your access token set up, will create a Mapbox map on a globe like this. But imagine being able to have a template like this where you could go in and customize every single element that you're looking at. So I could go in, and if I wanted the land to be a different color, I could change it. If I wanted the labels to be different color, if I wanted the state boundaries, the roads, buildings, lakes, I could change all of this. And then I can bring that styled information in, and I can have a completely custom base map. And so a lot of companies will use this. They'll bring in their brand standards and they will adopt brand standards for a base map, and they will have totally custom base maps through Mapbox that they use, which is really, really fun to work with. So Mapbox Studio is what it's called. We're not going to cover that directly today, but I saw a question about it. They said, can you use custom styles from Mapbox Studio to do this? Well, you absolutely can. So this is code that would get that done. Here I have a custom style, but that custom style I've made is completely blank. And so this isn't going to work for you if you don't have a Mapbox account set up. And so don't necessarily try to run this code, but it'd be, if there are future questions about it, feel free to send me a ping, but I'm not going to get into this whole process right now. But the idea behind it is, for those of you who are interested, instead of one of the built-in styles, I can supply the URL to a custom style that I've prepared and then pass that to the style argument. And that will allow me to create a custom styled map. And so this map, which I'll just kind of show you how it works because it will work on my machine. I have it commented out here. But if I run that myself, I can make something like this, where I have the blank background. You can see it. It's just gray in the background. And then I've added a hover tooltip. So I mentioned, if your audience has a general understanding of US geography, maybe that's not required, but your audience might be an international audience. It might, you can't necessarily assume. And so I've added the hover tooltip here where you say, okay, well, what's here? Oh, that's the District of Columbia. What's up here? That's Vermont, that sort of thing. So I'm providing some of that additional context that gets lost when I remove the base map. So from the MapLibra side of things, there's not, for MapLibra, an equivalent Mapbox Studio. And so what you can do, and this is a little bit more advanced, but I'm providing the code for you, so feel free to use it, is you can build a custom style from scratch. And this is how it gets formatted in R. So feel free just to copy paste this and use it if you need a blank base map. And so I can pass in this custom built base map from scratch as my background. And so in the example I'm showing here, I am doing it in the Mercator projection. And so it's going to look like this. But I get that blank background. And this might be suitable for the visualization purposes that you're interested in. If you wanted to add a set projection globe, you could do that. And I'd be willing to bet that MapLibra will support other projections in the future. I can have my globe view here. Obviously outside of the globe, it's still white, but I can set my zoom where I have a pretty decent looking map, and it has that nice gray background so that I'm not so worried about, Puerto Rico and the Gulf of Mexico or Hawaii over Mexico itself, that sort of thing. A couple questions about shift geometry that I'll go ahead and answer now. Does shift geometry work for countries other than the US? It does not. Uh, shift geometry is a relatively bespoke function that specifically solves problems for the US. And because it belongs to the tidyverse package which focuses on US data, that same approach I use in shift geometry could well be used for other countries. Like a great example might be Portugal. Portugal has islands that are very, very far from, the actual country. Or France is another example that comes to mind, where you have territories that are pretty distant from from mainland France. And so, in this particular case, it, you might consider writing a function that does something similar, but places those territories in specific locations that are going to correspond to what you would want to visualize for that country. Another question, does shift geometry work for other territories such as Guam, American Samoa? It does not. I've thought about this, but I have not included it in part because um, those data sets, so data for Guam, American Samoa, Virgin Islands, are not found in the same data sets that the 50 states plus DC and Puerto Rico are found in. So if you go to the ACS, you're not getting data for the island territories. Those are in specific separate data sets. They have their own decennial census files. And so it didn't necessarily, from a practical sense, make sense to include it. And I wasn't 100% sure where to put it. Some people have requested that feature. And, frankly, one of the great things about open source software is anybody can go in and they can, what's called fork my repository, make their own copy of it, make a modification, and then suggest a change. So, that's something I would definitely be open to, but I haven't adopted that yet in Tigris. Let's see here. Looking at the questions. We answered a few of those already, so let's go ahead and keep moving through. All right, so next use case, so national mapping for states. That's something you're going to want to do a lot. But a question that I've gotten, and it's been a use case that I've thought of at times as well, is what about national mapping for small areas where you want to show tens of thousands of data points at once? There are a variety of different use cases for this. Let's say I wanted to show census results for the whole country, small areas, because neighborhood level analysis is really interesting. Or, those great precinct level election maps that the New York Times puts out after every presidential election, where you can see neighborhood level patterns, which frankly are extraordinarily interesting. Especially, state level analysis, yes, that matters for the electoral college, but it obscures a lot of what's going on internally. Neighborhood level election analysis is really interesting, but it requires displaying a ton of data at once, and that can be difficult. So we're going to take a look at something here. We're going to try to map median household income for all US Census tracts. And that's a tricky thing to do. First things first, we got to pull down all of the data. So I don't have this data file available for you. It was just too big to host. So what I'm going to do is I'm going to show you this code. I think it'll be useful for you. Now, it takes a little bit of processing to get this done, but what this will do, I'm going to uncomment this here. This will show you how to get all of the data by census tract for the entire US. So I'm going to run this code, and you'll notice it gives me the message fetching tract data by state and combining the result. So what it's doing, because you can't pull down all the data for the entire US at the census tract level. I see one person asking if I'm muted. I'm not showing myself muted, but please do ping if there are any audio issues coming through. what this is doing is it's using functionality in Tidy Census internally to iteratively step through state by state and pull down the data state by state and then combine it. You'll notice it takes a few moments to compute, and that is because we're having to do all of those API calls. We've grabbed all of our data here, and we can take a quick look at our data now. And you'll notice we have a ton of data we're working with, 85,000 plus census tracts. That's a whole lot of data. But being able to visualize all that information ends up being pretty interesting, because if I'm just visualizing by state, that's going to obscure a lot of within state patterns. And I may want to make a lot of data available to my users. So how do you do this? Just a heads up, if you're using the Posit Cloud environment, your Posit Cloud environment will likely choke on this process. So I would say just follow along and kind of watch and see what I'm doing, and then potentially try installing on your own computer and trying that out. But the default Posit Cloud environment is likely not going to be able to run this. So let's jump back to the slides here and talk about what an initial tract map would look like. So let's initialize MapLibra, focused on the US. We're going to focus on the continental US here. We're going to add the fill layer with an interpolate expression, fairly similar to what we've learned how to do already. Can MapLibra map all 85,000 census tracts? Let's give it a try. It's not going to map instantly. We're drawing a whole lot of data right now. But it does a pretty decent job with it. Here we have our national map mapping all of the census tracts. There's Alaska, there's Hawaii, and it's reasonably performant. However, you're likely noticing a problem. Look at all of the cities, the big cities. There are holes. New York, Chicago, Minneapolis, Dallas, Fort Worth, Houston. There are holes in those cities. I can zoom in. Let's say I zoom into Atlanta, and the holes go away. But when I zoom out, the holes reappear. And you might say, well, what's going on here? Why is this happening? It's a great question. And it allows us to delve a little bit more into the technical details of how MapLibra and Mapbox display data. So whenever you're visualizing large amounts of data, even though you're using WebGL and really advanced features in your web browser to do that, the libraries are still always thinking about optimizing performance. And rendering all of that data on the fly without making your browser crash is pretty difficult. And so the libraries make design decisions to handle this. So what MapLibra does is it uses dynamic simplification with the famous Douglas Pucher simplification algorithm. And this is a little bit in the weeds for those of you who are new to GIS. But what Douglas Pucher does is, I mean, it's probably the most common generalization or simplification algorithm used. And the general idea is that we're making the shapes simpler as we zoom out. And Douglas Pucher has a tolerance. You know, a tolerance is fundamental to the algorithm. It's basically going to be the minimum threshold at which we start removing data, removing points. And so the default tolerance used in MapLibra and in Mapbox is 0.375, which refers to the underlying map tiles. That's not necessarily meaningful to you, but at zoom level 3, so what was the initial map view when we were zoomed out, that corresponds to about 5.6 kilometers. And many census tracts in large cities are actually smaller in perimeter or in diameter, I suppose, than 5.6 kilometers. And so they get dropped entirely. In this particular case, you kind of have to weigh the trade-offs. If I'm looking at my map here, you'll notice that I'm displaying 85,000 census tracts pretty performantly. It's quite fast. And that's a whole lot of data that I'm displaying with minimal lag time at all. But zooming out here and having these holes, from a visual representation standpoint, maybe is not great. And I could explain this to a viewer, but your average viewer, I mean, you're a very technically literate group. This might have been some new concepts for many of you. If you're displaying this, say, for a major media publication to an average user, they're not going to care about those technical details. What they are going to care about is the fact that it looks like your map has holes in it. So how do you resolve that? I want to show you a couple of different options. One is you can set the tolerance. So if I can change the tolerance, and so what you've learned how to do is add a source within a layer function. So when I'm adding a source, typically I've specified a data set as a source. You can actually use the add source function in mapgl to add the source separately. And that allows you to do add source level arguments. So if I use add source with the tolerance set to 0, and then I display my data, I want to show you what this looks like. It's going to take a little bit longer for the map to render, because now it's having to render every single census tract when zoomed out. We'll wait for it just a little bit here, and you'll notice how it's a little bit chunky when it renders. But as you can see, all of the cities are now filled in. It just took a little longer to render. And when I zoom and pan around the map, it's reasonably performant, but it can't render everything at once. Again, it needs to do it in chunks. Whereas in the previous map, I didn't have to worry about this. So I see the trade-offs, right? I can zoom all the way out, and I am not dropping anything at all. Even those tiny little tracks in New York City, I'm not dropping them at all when I'm zoomed out. But when I zoom in and I try to zoom out and in and out quickly, my performance is going to be degraded. And so you have to kind of think about those trade-offs. You don't have the holes at small zooms. That's good. But you have slower loading times and poorer map performance. If you have users with slow internet connections, that might be a real struggle. And then you have the same issue. So is there a compromise solution to this? Well, you kind of have to ask yourself the question, do you need all that detail when you're zoomed out? You might consider when you're zoomed out, because frankly, if I'm way zoomed out like this, yes, I don't have holes in New York, but can I actually tell what's happening in New York at this zoom level? No, I can't. I mean, I can squint and kind of see some dark blues and some light yellows, but frankly, I have no idea. It is not clear to me what is what. And so a compromise solution might be, because census data is available at a variety of different geographies, show a less granular geography when zoomed out and show a more granular geography when zoomed in. So let's take a look at how to do this. I'm going to pull down some county data, and I'm going to skip through this a little bit quicker for purposes of time. I'm going to pull down the same county data. And then this code is verbose, but I want to step through it with you. I'm going to initialize the map, set the projection. I'm going to add my census tracts, but I'm going to specify a minimum zoom of 8, which means that data will not display prior to zoom level 8. And so web maps, by the way, you can zoomed all the way out where you can see the globe multiple times over. That's zoom level 0. And then you can zoom all the way into a zoom level of 22, where you can basically see someone's backyard. I'm then going to add a second fill layer using the county income, the same styling, but with a maximum zoom of 7.99. So once my map hits and transitions from 7.99 to 8, it's going to replace the counties with the census tracts. And then I'll throw a legend in there as well for good measure. Let's run that. I'm rendering a lot of data, so the load time is going to take a second. But let me show you what this does. Go back to my viewer here. So here now, when I'm zoomed out, these are counties. And counties are much more legible when zoomed out. But now let's zoom in here, say to Washington, D.C. I'm still at the county level, still at the county, still at the county. And as I get a little closer, you'll notice I transition to census tracts. So when I'm zoomed out, it's counties. When I'm zoomed in, I get the richness of the census tracts. And so you can really see that, for example, in some of the counties around DC, relatively high income, but you have even higher income areas inside of those counties. And so you have a dynamic map that's bringing in all of this data and is resolving the holes issue. And also, you'll notice that the performance now is much better when zoomed out because I'm only showing 3,000 some counties instead of 85,000 census tracts. So I find that to be a fun and compelling example. I've seen major publications do that sort of thing as well. All right. In the last bit of time, I want to show you a couple examples that are more advanced from a code standpoint, but are pretty fun to take a look at. So bear with me. I'm not going to step through the code in tremendous detail, but I want to show you a couple different use cases for how you might compare demographic change over time. So one of the challenges of comparing small areas over time, so census tract boundaries change from decennial census to decennial census. And so there's not an easy one-to-one comparison available for small areas. And so how do you show change over time? I want to show you a really fun feature in mapgl, which allows you to integrate something called a comparison widget, and it gets you a slider between two maps. And so a basic example of how compare works, I just want to show you real quick before I chunk through all of this code. The compare function allows you to take two maps, and I'll paste this code into the chat. So let's say I have one map. I'm going to call it map 1, and I'm just going to do map Libra. And then I'm going to do map 2 is map Libra, and I'll do the style equals Cardo style dark matter. And so my original map uses the Voyager style. My second map uses the dark matter style. If I use the compare function, I can do compare M1 and M2. I then, got to define all of that. Map 1 and map 2. Once I run that, I now have a slider that allows me to swipe between the two different maps if I want to compare what one map looks like versus another. And you can add your data to this as well, which I'll show you. So in this advanced example, what I'm going to be doing, and I don't have time to go step through the code in tremendous detail, but what we're going to do is we're going to pull down population data for 2010 and 2020 by census tract in the Dallas-Fort Worth region. And we are going to calculate population density. So, this code is a little bit more advanced. So I'm not going to go through that in tremendous detail, but use it as a learning resource to show how you can calculate something like a population density. So I'm going to pull through, I'm going to just run through all this code here. And what you're going to see here is I have about 1,300 census tracts in 2010 in the Dallas-Fort Worth region, and I have about 1,700 in 2020. So I've subdivided up a bunch of the census tracts. So how might I use this comparison slider to show changes in population density? Well, for one, I could make a couple maps and use compare. I've got the legend here. And then I could swipe between them. And you'll notice here in Uptown Dallas, the density has gotten greater between 2010 and 2020. An issue with this, however, even though it's interesting, is the smaller high density tracks can be hard to see. So let's try something fun. And I haven't shown you this yet, but this is one of the reasons that I think mapgl is a very compelling solution for your mapping in R. And so jumping back here, a potential solution is to use 3D extrusions, where we pull up the shape of each census tract based on its population density. And so I'm going to show you how that works. We're going to go ahead and run this through for the 3D. And if I hold down the control key and drag my cursor, you now notice I have a 3D view that extrudes the height of the various census tracts based on their densities. And so I can swipe between. Here's the view in 2010. I swipe across, and I can really see the expansion up here in the north of Dallas. So this was population density in 2010. I swipe across, and that's the density in 2020. So that's a fun example. I know it's a little bit more complex of an example, but that's a fun one to leave you with to give you a sense of some of the creative and powerful visualizations of census data you can create with some of these tools. Again, I really appreciate your time. 230 of you made it all the way to the end, and that blows me away. So thanks to all of you who have attended any part of any of these workshops. And thank you so much to Bill, Jessica, and the SSDan team. Bill, I'm going to hand it back to you to close things out. Bill, you're on mute.
All right, that should do it. Kyle, thank you very much. As I promised those people at the beginning, Kyle wanted to end with a big finish. And that 3D map that he showed really was a big finish after doing the 85,000 census tracts in one swipe too. So I think those of you who have stayed with us really have learned a lot. Some of it, you'll have to work on a little bit if you've seen it for the first time. But this is really cutting edge stuff using all of the huge data that are available with the census, the 2020 census, 2010 census, and others. This has been a wonderful, wonderful series that we've had these last 3 webinars with Kyle. And I want to thank him for it. And I want to remind all of you that in another day or so, you'll get an email from us, which will allow you to access the videos for each of the 3-hour webinars that we had. The first on the American Community Survey, the 2023 American Community Survey, analyzing it with R. The second, analyzing the 2020 census with R. And then today's on mapping and spatial analysis of census data with R. I think this will give you a lot to go on. Again, thank you, Kyle. Thank you all from wherever you've been in being part of this. We really appreciate it, and wish you a good rest of the day.
All right. Thanks again, everyone. Take care.